Hi there. In this video, what I want to look at is just generally speaking, when does a function have a discontinuity in it? Excuse me, I am sorry about that. Uh, okay, so again, when does a function have a discontinuity? When is it not continuous across the entire real number line? Well, what I found in most calculus books, you're going to run into three main types of I don't know what you would call them. Three main scenarios where discontinuities are going to be introduced. And the first one, I just call it division by zero. Okay, and let's just go ahead and look at a function here, an example. If I have a function and I have a domain violation in the denominator. In other words, clearly here 1 is not a member of my domain. Okay, I end up, if x was 1, I would end up dividing by 0, and that's a domain violation. Okay, it turns out, if you think back to pre-calculus or algebra 2 trig, that we're going to get a vertical asymptote at x equals 1. Okay, so we're going to have a discontinuity at this vertical asymptote. That would be a non-removable discontinuity. Another example of discontinuities popping up because of division by 0, we'll use g this time. Suppose I had the following: x plus 2 over, and I'm just going to write it in factored form right away, x plus 2 times x minus 1 in the denominator. Well, what is the domain of this function? The domain is going to be all the real numbers with the exception of negative 2, because that would make this 0, and 0 times this would be 0, so you can't divide by 0, so negative 2 is not there. But positive 1 is also not a member of my domain. Now, before you jump right to say that we have two vertical asymptotes here, I want you to notice that this x plus 2 up here can actually reduce with the x plus 2 down below. Okay, this is how I remember what a removable discontinuity is. Okay, if I simplify this function, I get a new function. Okay, this new function looks a lot like this guy up here. And we know that this guy just has a non-removable discontinuity at 1, which is our vertical asymptote. Okay, but remember, the original function is not 1 over x minus 1. It's really this thing, where negative 2 was not a member of my domain. So what's the difference? What's the difference between this and this? Well, it's effectively going to be the same graph, okay, with the exception of one minor detail. Okay, we know we have an asymptote at 1, and we also know we're going to have a horizontal asymptote at 0. I won't go into the why of that right now, but trust me, there's a horizontal asymptote at 0. Okay, this right here is the graph of 1 over x minus 1. Okay, but we know that negative 2 is not in our domain, so what happens? Okay, well, at negative 2, maybe negative 2 is right here, we would actually get a little hole in our graph. Okay, we would call this a removable discontinuity, just as if we've kind of removed or plucked out a small piece of the graph. Okay, so these are the two main types of discontinuities you will find when you get division by 0 in your function. Okay, moving on to the next one is a piecewise function. More often than not, you're most likely going to get a discontinuity of some sort if you have a piecewise function. And let me say that just because you have a piecewise function doesn't mean that you will have a discontinuity. It just means that you can. Okay, so let's just think of two functions here. Let's stick with x minus 1, which that's a continuous function. That's a line. And let's just say that is going to be our function for all x greater than or equal to 0. Let's pick out another one. Let's try negative x for all x that are less than 0. Okay, well, here's a piecewise function, and again, just because it's a piecewise function doesn't mean that it's going to have a discontinuity, but it could. And since this is a continuous function and this is a continuous function, the only possible place this thing could possibly be discontinuous at is at this point of 0. Okay, so if I were to quickly sketch this, it's not too difficult to sketch. I have two linear functions here. Looks like I have a y-intercept down here at -1 and then a slope of 1. Okay, so this part of the graph represents this x minus 1. And remember, we get mapped to that line for all x's that are 0 and bigger. If we're less than 0, though, we get sent to this other line. Well, where's this other line at? Well, it has a y-intercept of 0, but remember 0 doesn't get mapped to there, so we're going to put a hole there. And its slope is -1. So all of the x's that are less than 0 get mapped to this line right here. Okay, so you can clearly see that if I were to just sketch this graph, I would have to lift my pencil up at 0 to complete my graph. So we have a discontinuity at this piece right here. Now, one way to think about this is, what would you have to do to this graph? What small change could you make in order to make this a continuous function? Well, you could do a couple of things. You could take this line right here and you could shift it up 1. In other words, if you just called this graph up here x, then this would actually look a whole lot like our absolute value function, okay, a v. It would just come down here, touch the origin, and then bounce back up. Okay, or you could take this guy and you could shift him down 1 so that he effectively has a y-intercept now as well as -1. You would just add a -1 here. Okay, the third one is the greatest integer function. What's the greatest integer function? Well, some people call it the step function. Different textbooks write it slightly differently, but this is perhaps the most common way. Okay, there's the greatest integer function. And really, all the greatest integer function does is effectively chop the decimal off. Okay, so as you're moving on a number line from left to right, excuse me, as you're moving on a number line from left to right, you simply ask yourself, what was the last whole number that you ran into? Best way to see this is just to build a table of values. Okay, so if this is x and this is f of x, okay, and you plugged in a positive 1.1. Okay, well, think about it. If you're on a number line, and here's 0, and here's 1, and here's 2, and you're at 1.1. Where's 1.1? 1.1 is right here. Well, as I'm moving across the number line and I get to 1.1, ask yourself, what was the last whole number that you ran into? And it was positive 1. Okay, if I'm at 2.03, okay, well, as you're moving left to right on the number line and you get to 2.03, which might be about right there, what was the last whole number you ran into? Well, it was 2. Okay, well, what if you're negative? Okay, here's -1 here. Maybe this is -2. Okay, let's pick one. Let's pick -1.5. Okay, well, let's just see this. As I'm moving along the number line and I get to -1.5, here's -1.5. Okay, well, where was the last whole number that I ran into? Well, it was -2. Okay, so you get an idea that you're always going to get a whole number here. Well, what does that function look like if we graphed it? You could simply plot all these numbers, or just kind of think in your head that the same process that we got these numbers, we can just do this on the graph over here. So where does 0 go to? Well, 0 is going to get mapped to 0. Where does 0.5 go to? Well, 0.5 is also going to go to 0. In fact, all of these numbers before we get to 1 go to 0 until we get to 1. Where does 1 get mapped to? Well, what's the last whole number you get to when you land on 1, before you land on 1? Well, you're on 1, so it gets mapped to 1. 1.1 gets mapped to 1. 1.2 gets mapped to 1 until we get to 2. This is 2, this is 1. Okay, so all of these values now are going to get mapped to 2 until we get to 3. And going back the other way, this is going to do something very similar. We get a hole here, and this is at -1. I'll do one more here. This is down at -2, and this is at -2. Okay, if this is confusing to you, maybe just come back to this number line or build some more tables. If you don't see why this line is down here, again, just try some values here. Try -1.9. Okay, -1.9 is right here. Well, as I'm moving from left to right on the number line, and I get to -1.9, which is right here, what was the last whole number that I ran into? It was -2. So -1.9 gets mapped to -2. Okay, so those are the 3 main ways that you can have a discontinuity in your function. Division by 0, piecewise function, or the greatest integer function. This division by 0 I usually call a domain violation, and I can hear some of you now, you're saying, well, what about the tangent function or the secant function? And really, if you stop and think about it, our tangent function is just division by 0. That's why we get all those asymptotes when you graph a tangent function. Remember, tangent is really the sine over the cosine. Okay, so this fits into this category right here of getting some discontinuities due to division by 0. Okay, so wherever cosine is 0, you're going to have a vertical asymptote and therefore a non-removable discontinuity. Okay, so division by 0, piecewise functions, greatest integer functions. I'm sure there's others out there, but those are about the 3 main types that you're going to run into in a typical calculus course. Okay, thanks for watching. I hope that made sense, and we'll see you around.